So we've spent some time on impulse and change of momentum and the meaning of center of mass motion. But now let's talk about momentum conservation, a very important concept in physics and engineering in particular, probably, again, in all sciences, these concepts of conservation or conserved quantities. So let's talk about momentum conservation. Let me take our equation where we left off in our derivations and think about a little more about it. This equation holds for a single mass or a system of masses if you're exerting net forces on many different masses. That's necessary to understand in order to understand conservation of momentum, that it's for a system, not necessarily just a single mass. Before I go much further with the equation, let's think about this concept of a system. Let's take two people. If we were in the classroom right now, we could show this, but let's put them in rolling chairs. Let's take two people, put them in rolling chairs. Okay, so there's one person, and here's another person. Addie and Zelda are in two rolling chairs, and they're actually big enough so that they can push on each other, let's assume that we're on a frictionless surface, or the rolling chairs makes it so we don't have to worry too much about the friction. And let's just imagine that Addie and Zelda push on each other. If they push on each other, what's going to happen to the chairs, right? If Addie pushes on Zelda, then by Newton's third law, notice that Zelda has to push back on Addie whether she wants to or not. What happens is Zelda goes that way and Addie goes that way. Hopefully that's pretty clear. Excuse me. So let's just ask about Zelda. Is Zelda's momentum conserved? What does it mean for momentum to be conserved? During this little push fight, is Zelda's momentum conserved? And the answer is no, because Zelda goes from rest to some velocity v, and so Zelda's initial momentum is 0, and Zelda's final momentum is m times v final, and so Zelda's change in momentum, delta p, pf minus p initial, is not equal to 0. So the fact that the momentum changes means that it is not conserved. So Zelda's momentum is not conserved during this process. Why is Zelda's momentum not conserved? Zelda's momentum is not conserved, it turns out, because there is some kind of external force on the system of Zelda. We'll explain that. Well, actually, we should be able to see this, right? There's an impulse. There's an impulse on Zelda's system, right? If the system is Zelda on the chair, then there's an impulse on Zelda. There's a net force on Zelda that's exerted for a certain amount of time to change her momentum. And then we ask the same question for Addie. Is Addie's momentum conserved? And the answer is no. Addie's momentum is not conserved either. Addie's momentum starts at 0 and ends at mv, blah, blah, blah. Maybe a different mv because she might be a different m, but delta p is not 0 and Addie's momentum is not conserved. But what about the system? What if we don't treat Addie and Zelda separately, but we treat them as a system and treat Addie and Zelda as a system? Is the momentum of that system conserved? Well, the system, initially, they're both sitting still, so the total momentum of the system is the momentum of Addie initial plus the momentum of Zelda initial. And since they're sitting still, each of those momentum, mass of Addie times the velocity, initial velocity of Addie, plus the mass of Zelda times the initial velocity of Zelda. And since the initial velocities are 0, equals 0. So the total initial momentum is 0. What about the final momentum? Is the total final momentum equal to 0? Well, I'm not 100% sure. To know that, we need to know the final velocities of Addie and Zelda, but the total final momentum of the system of Addie plus Zelda is the final momentum of Addie plus the final momentum of Zelda, and that equals m Addie v Addie final plus m Zelda v Zelda final. So we need to know various things about the system in order to know if momentum final is conserved. I'm going to do a little bit of hand waving rather than writing everything down. But let's just imagine that Zelda pushes on Addy with a force F push, like we said. And Zelda pushes on Addy with a force F push for a time delta t. So the impulse on Addy, F push delta t, is actually equal to the impulse on Zelda, F push delta t, because they're pushing on each other, so they got to be pushing on each other by Newton's third law with the same force, and they're pushing on each other for the same time because they're pushing on each other. So they each exert the same impulse on each other. So because they each exert the same impulse on each other, they're each exerting the same change in momentum on each other, because impulse equals change in momentum. So so that means we don't actually need to know this. The change in momentum of Addy must equal negative the change in momentum of Zelda. They're each exerting the same impulse, but in the opposite direction. That's the only thing that you got to realize, right? Look at the picture, it's in the opposite direction. So because it's the same impulse in the opposite direction, Newton's third law, equal forces in the opposite direction, then it's the same change in momentum, but in the opposite direction. And because it's because delta A sub P, the change in momentum of Addy equals minus the change in momentum of Zelda, we don't actually need to know this. All we need to know is, so that means that P Addy final is equal to minus P Zelda final. And because they're equal, then it's P. We can replace P Zaddy, because we can replace the final momentum of Zelda with negative of the final momentum of Addy, and the total final momentum must therefore be 0. In other words, what we've just shown is that the momentum of Zelda in this direction, P final, is equal to the momentum of Addy in this direction, P final. Those two are the same thing. That's what we've shown. And so that means the total final momentum must also be 0 because momentum is a vector. Yes, they're both moving. They were initially not moving, and they both are moving, but the momentum of the system adds to 0. Therefore, is momentum conserved for the system? It started at 0, it finished at 0. Didn't need to be 0, but it's conserved because these are equal to each other. They are equal. Therefore, momentum total is conserved. And we could say, so now we can use the fact that the momentum total is conserved. We know that the total final momentum is 0. If I asked a second question and said, what are the speeds of Zelda and Addy? We say, so now we know M Addy, V Addy, final, plus M Zelda, V Zelda, final, because that was the total momentum, is equal to 0. So as long as I know their masses, then I know their speeds. Okay, so because we know they're in the opposite direction. But if I said, Addy was twice the, do I know their speeds? I'm sorry, I don't. I only know their relative speeds. If Addy is twice the mass of Zelda, then Addy's speed is half that of Zelda's. If they're the same mass, then they're the same speed. But depending on how hard they're pushing on each other, right, that's what gives you how fast the speed is. So we would need to know, in order to know the actual speed, we need to know the force of the push. But anyway, okay. But we can use momentum conservation if we know enough information to therefore find final speeds after some kind of, in this case, this is actually sort of like a collision, but it's a backwards collision, right? It's an explosion, which is the opposite of a collision. And that's what we're going to do, is we're going to use momentum conservation to figure out what happens in explosions or collisions. An explosion, not like boom, big boom, but the opposite of a collision. That's what we're going to use momentum conservation for. Momentum conservation is all about collisions and what happens in collisions or backwards collisions. Come back to this concept that momentum is conserved. That's super important. That's the important concept here, is that the momentum is conserved. So remember, the momentum was not conserved for Zelda or Addy by themselves, but momentum is conserved for the whole system. What is the quality? Quality was the wrong word. What is the requirement for momentum conservation? What is the requirement for momentum conservation? It is actually the requirement for momentum conservation you can actually see from our top equation here, right? Our equation that we started with. We showed that Zelda's momentum changed because Addy exerted a net force on her. We showed that Addie's momentum changed because Zelda exerted a net force on her. So we call that an external force to the system, right? So there was an external force on Zelda. There was an external force on Zelda, which was Addie's force. There was an external force on Addie, which was Zelda's force. But when you look at the whole system, when you look at Addie and Zelda together, then there are no external forces on the system, right? These forces here are what are called internal forces. They're internal forces. There's no external force on the system. And it turns out that what is the net force on the system of Addie plus Zelda? The net force. There are forces. It doesn't mean there's no forces, but what's the net force? Well, Addie pushes Zelda with a force F push. Zelda pushes Addie with a force of F push. What's the relationship between those two forces? They are, by Newton's third law, necessarily equal and opposite. So the internal net force is zero. They add to zero. Let's be a little clearer here. Take the equation that we started with, and we can just break up the net force. We can say, oh, okay, so some of the forces are going to be internal, and some of the forces are going to be external. Those are the only two choices, internal or external. There's nothing else. So the net force is the internal net force plus the external net force. And then we can say, oh, the internal net force must always be zero. Internal forces in a system must always be zero. Why? Because of Newton's third law. Newton's third law says that if one object exerts a force on another object, the other object exerts a force back on the first object that is equal and opposite. And so if Addie exerts a force on Zelda and Zelda exerts the equal and opposite force back on Addie, and the system is Addie plus Zelda, then those two forces must add to zero. So internal forces are always add to zero. Let me just do hold on a second. So this is an interesting concept, right? Think about your body, right? Your body actually has a bunch of different parts. And so your right hand can exert a force on your left hand. You can push your head. You can lift up your pants, whatever. You can exert forces because there's actually different objects. But because your body is a single system, each of those forces that you exert on yourself is an internal force. So just take your two hands and push on your hand, one hand with the other hand. I'm doing it. I know you can't see me. And you can push harder and your arms will go one way. You can push harder and your arms in the other direction. Your arms will go the other way. But the net internal force is always zero. And what that means is that you can never move your center of mass. Internal forces can't move a center of mass. In other words, they can't change a momentum. Because remember, changing momentum means that you're changing the center of mass. You can never move the center of mass. So I can push my arms left and right all day long, but I can't change the center of mass of my body. I can't move the center of mass of my body until I get an external force, like pushing off on the floor when you're walking. And this is the concept of bootstrapping. Have you ever heard of the concept of bootstrapping? Bootstrapping means that you can't lift yourself up by your bootstraps. That's an old saying. You can't lift yourself up by your bootstraps. And think of shoelaces or just grab onto your shoes. If you lift upwards on your shoes, can you lift yourself off the floor? Try it. Can you lift yourself off the floor by picking up on your shoes with your hands? No, of course you can't. But you can't because you have enough strength to lift your body off the floor, but you can't lift your body off the floor if it's only internal forces. And that's what it means. That's what bootstrapping means. And it's an interesting because it was adopted by the computer by the computer community. And have you ever heard of booting your computer? When you boot up your computer, what your computer is doing is it's not literally exerting a force on itself, but it is telling itself how to run itself. And it's like bootstrapping. It's like you sort of lifting yourself up without an external force. It's actually, that's where the concept of booting up a computer comes from. Okay, anyway, so let's come back to our equation. So our equation tells us that only an external force can change momentum. Only an external force on a system can change momentum. That the net external force is what changes momentum. And if there is no net external force, therefore, what can you say about the momentum? Therefore, delta P must equal zero. Therefore, not P equals 0, but this means P for the system that we're talking about is conserved, whether the system is a single body or a bunch of bodies. The momentum for the system is conserved if there's no net external force on the system. This is key. And we are going to use this for the rest of the semester to solve momentum conservation problems.